We have handed back exam printouts, and I want to go through some comments just to start getting everybody organized. We have another round of special study groups coming up. They'll be running next week. Next week, you actually have classes on Monday, but not for this course. Your other Monday, Wednesday, Friday classes, you'll have a Monday class, and then Tuesday is study day for those of you that are newbies at UCF. And then Wednesday is the beginning of final exam week. So SSG, I've set up a schedule page for you, and Kate Tomlinson, a bunch of other people. Here's some more. Miles, Bethany, Caroline, Alexia, they've already given me their data, and more of them will be announced. So Lindsay and Morgan, the rest of those guys will be getting their data in for that. So that schedule page has a red clicker on it, or excuse me, not a red clicker, but a red swing line stapler. And so you can, when you see that, you'll know you're on the schedule page. So start looking at the schedule, see what you want to try to get. And sign-ups are going to go on Friday evening again. And I'll announce the exact time on Thursday in lecture. And so, you know, it was pretty much a Buffalo stampede at about 7:01 last time. So be ready. And if you're in group one, you're still in group one, you still have first dibs. Everybody's going to wait from 5 until 7 or from 6 until 8, whatever I set it to be. And I'll let you know on Thursday. So, but at about 7:05, if I open it at 7, by 7:05, everything's pretty much going to be. And don't sign up for something you cannot go to. I'm going to be I was not happy about it. There was 3 students that signed up and took your spot. If you wanted to get points, bonus points for studying, and a higher grade, which I noticed several of you did higher on your grades, you couldn't do that because of these 3 individuals. So don't let that be the tale told about you. All right. We have another thing running. Probably I'll open it up tomorrow. It's going to look like this. A bonus points discussion area, and it's actually going to be for bonus points. You're going to create a multiple choice question, possibly for the final exam. If it's good enough, I'll use it. And sometimes I use quite a few of them because there's quite a few, but it has to be really good. It's in discussions. And so Nisha, who's now in web courses finally, and Darianne and I will be reading it. I'll be grading it, but the 3 of us will be commenting on it. And if it's good enough for you to use, you get 1 question. So make it a good one. And you can earn 2 bonus points for that. Now, for those of you that missed out on special study groups last time, this doesn't totally make up for it, but everybody can get this if you have a good question. And if the question that you write is not quite good enough, I'll comment on it and you can revise it. And that's a way of learning. And also, everybody that reads that area of web courses, that discussion thread, is going to benefit as well. So now you won't know before the exam whether I give you bonus points. You won't know if I use your question. And don't let any comments of mine deceive you into thinking, oh yeah, he likes my question. It's in, I got it. You know, you won't know. I might not say hardly anything about it. Just, you know, if I really like it, and if, oh man, this thing is so good, I'm not going to I might not even comment on it, just so that you don't even, you know, get any tip-offs. Okay, but if you have a question, and like you didn't quite get the right answer, or you did it, in a way that's not quite kosher, we'll work it out, and you can revise it and stuff. And maybe your revised one will be good for bonus points. There was a question up here. Yeah.
So your questions, there's a cumulative one, so it can be from February.
It could be on any topic from August through the end of this week. Okay, so it just has to be really good, and just be creative. It's actually kind of a fun way to get some bonus points and to study. And if you think about it, if you write a question and I include it, you'll already know the answer to one of the questions. So this is really worth 3 points, 2 bonus points, and then 1 more point on the exam that you might not get. But you will, because you know this. And so will everybody that studies it. So even if I don't select your question, if you study all the questions in this discussion area, because there will probably be a few, you'll have studied questions that are going to be on the exam. I used 10 questions once. I might use 20 this time, because you guys are pretty smart this semester. All right, that's right. We got a guy up here in the front saying, "Yep, that's me, baby." Yeah. No, it's good. But seriously, if it's good, I'll use them. I just won't tell you. You won't find out till the exam. But then you'll know. It's good. It'll work out good. And it's a traditional thing. Now, the other thing I don't have on the screen here, but I'll also mention, is this Friday you'll have a regular homework assignment, and then I'll also set up a big mega review homework assignment due the 9th, December 9th, that you can work on. And I'll convert that into a couple, 3 bonus points. So again, if you didn't get any SSG, or if you have a little bit of stinkiness in your clicker grade, this, and then the discussion area bonus points will kind of cover up some of that and help you out. Question all the way in the back. Where did you hear that? That's not in my syllabus. Is that on like another planet, or, Just study everything. Study like it's a midterm that covers everything. I don't know how. I've never ever said anything about the department in this class or any class writing the final exam. You must be thinking about some other class. All right. All right. Here. Let's get back down to business. We have a little bit shorter lecture today, but let's cover some ground. I want to go back and talk about Rutherford and the Rutherford model. Jacob, please. We've talked about this before. He fired some of these mysterious alpha particles from a radioactive source into a thin gold foil. This is the stuff we talked about previously. And he detected backscattering. And he was also able to analyze all the angles and speeds and the electrical potential energy and so forth. And he was able to place an upper limit on the size of the gold nucleus. In other words, he was able to say the gold nucleus cannot be any bigger than this distance. And he found that it was very teeny compared to the atom. And at most, the atom, the nucleus is 1/100,000th of the atom, diameter for diameter. All right, so from that he was able to suggest the planetary or Rutherford model of the atom, that the electrons were little teeny negative planets orbiting a positive nucleus that had a lot more mass. And just like orbits planets orbiting the sun. Only for this interaction, it's the Coulomb interaction. It's not gravitational. Now we're going to talk about this model, and here's a little this is kind of like an artist's concept, except it's not really to scale. But we're going to talk about the scale of electrons orbiting a tiny positive nucleus, and we're going to actually compare the nucleus to a basketball. So here we go. Let's work on this analogy. Now, Rutherford's calculations figured out that the nucleus and the atom are about 1 to 100,000. And that's diameter for diameter. So if the basketball is 1, what would be for the nucleus, then what would be the diameter of the atom at that scale? So there's our analogy. If the basketball is the analog of the nucleus, how big would the entire analog of the entire atom be? Okay, so there's our question. So in real life, a basketball is about 24 centimeters diameter, about 0.24 meters. So 100,000 of those is going to be 24,000 meters. Okay? And if you know your metric system, you know that that's 24 kilometers. So the 24 kilometers in the English system is about 14 miles. And that, my wonderful students, is about halfway across Orange County. All right? So, for example, the student union at UCF, if you go from the Starbucks in the student union to, they don't have a Starbucks there. So Subway in the student union to Starbucks out at the airport. I figured it out the other day. Here's a picture of it. Okay, so just make a note. Map, UCF to Orlando International. Here it is. From Subway in the student union to Starbucks at Terminal A. Yeah, that's about 21.554 kilometers. All right? And so the basketball is the nucleus. 24 kilometers is the diameter of the atom, analogous to that. So it's kind of incredible. The upshot is that most of the volume of an atom is empty space. And it makes you think, well, what does it mean for something to be solid? I thought, this table up here is pretty solid. I saw somebody in the back row. Ooh, somebody's knocking at the door, Dr. B. A tabletop is pretty solid, but really most of it's empty space. What? So here's what you're looking at. Here's the basketball, right? And so if you put it down here, somewhere in this, in this line, you're looking for a basketball. One basketball. Somewhere between here and the airport. But electrons know where it is. The electrons orbit that. And that is what an atom, and that's just a simple hydrogen atom. Now, other bigger atoms are a little bit tighter than that. They have a bigger nucleus, more positive charge, pulls those electrons in a little bit more tightly. The periodic table encodes a lot of that. But it makes you really wonder, what does it mean to be solid? Because atoms are mostly empty space. And that's according to Rutherford. Now here's another question to ask yourselves. Why don't those electrons, they're zipping around, why don't they radiate away some electromagnetic radiation? some Roy G. Biv or some ultraviolet, maybe a little bit of infrared, maybe a little bit of radio waves, microwaves. How about an X-ray or two? Why don't they do that? Why is an atom stable? Right? And this is the main topic for us today. We're going to try to work our way through the physics concepts that we have right now and try to apply them to this atom. The Rutherford model is out of date. It's obsolete. But we're going to get to the modern model, the quantum mechanics model of the atom today. But before we do that, I want to ask you a question about rainbows. And let me... Okay, here's your first question on iClicker. This optical device breaks up sunlight into a rainbow. Now, if you had sixth grade science class, you probably know the answer to this, and it's still true. At least one answer to this. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what we got here. Yeah, we're doing pretty good. Prism is correct, but actually, both of those are correct. Now, go ahead and make a note of both answers. Diffraction grating and prism. And a scientist, when he's trying to measure the wavelengths of light, will usually use a diffraction grating. But a prism will do. Sometimes you have really faint light, and a prism will absorb all of it, but a diffraction grating is sometimes the thing to use. And I'm glad to see most of you guys got that one right. Now, what do rainbows have to do with prisms and atoms? Well, you're going to find that because we're going to talk about the quantum theory of hydrogen. The hydrogen atom, is basically a proton and electron. So there's a little picture of them, and what the scientists who followed Rutherford suggested was that only a few orbital levels were permitted for the electron, and that there was a lowest level, this one right here, below which it could not exist. It was at that orbit or higher. And they said, if you think of the hydrogen atom, or atoms in general, as having this property, a ground state they call it. That lowest orbit is called the ground state orbit. Being the lowest thing, it's like the lowest point is the ground. And that's why they use that term. Only certain size orbits were permitted, and they were countable. In other words, there wasn't an infinity of orbital states. Only certain orbital sizes, and it depends on the orbital diameter. The orbital energy, if it was gravitational, GPE is controlled by how high you are above the surface of the Earth. If you have a big orbit or a tight orbit, that affects the GPE. Same thing here. All right. So the first thing is you number the orbits, and so for instance, when you go from orbital level 3 down to orbital level 2, you emit a photon of light. And for hydrogen, and this is for any atom, when you go from a high orbit to a lower one, the atom emits a photon of light. For hydrogen, when you go from the third level down to the second level, the photon is in the visible range and it's red. It's called H alpha. Very famous color. It's like the distinguishing color of hydrogen across the visible universe. Now, the guys that kind of figured this out were these two guys, Niels Bohr from Denmark and Albert Einstein from Germany. And here's kind of the summary of their theory. You number the orbits. As the electron drops to a lower electrical potential energy, so it's losing potential energy, it emits a photon with that same change in potential. So delta EPE for this jump goes into the energy of the photon. And if you read in Chapter 8, I've highlighted one of the formulas for that. And we'll probably talk a little bit more about that on Thursday. So this is the quantum theory of hydrogen, suggested by Niels Bohr and kind of worked out between him and Albert Einstein. And so basically what they were trying to do was figure out this. This is the spectrum of hydrogen. If you have a tube, a glass tube filled with a little bit of hydrogen, and you zap it between two high voltage terminals, okay, it'll produce light. And then if you put that light, Nicole, through a prism or a diffraction grating, you get this set of colors. Go ahead and, I don't know how you draw that, but H alpha, H beta, H gamma, and H delta, those are the Roy G. Biv colors that hydrogen produces, and only those colors. And there's actually an H epsilon here really down in the purples. You can barely see it. It's not very bright. Okay, now H alpha is for the orbital drop from n equals 3 down to n equals 2. H beta, one of the other colors that hydrogen produces, is from n equals 4 down to n equals 2. Okay? So from the fourth level up down to the second level, it's kind of a, I don't know, kind of an aqua colored photon. And then H gamma, that's n equals 5 down to n equals 2. And they used the Coulomb force law and the whole idea of potential energy, and they figured out it was exact. They were able to figure out the precise wavelengths, just right down to the number. H delta, that's n equals 6 down to n equals 2. And the important thing about this is something that they knew from the middle of the 1800s. So I guess maybe after the Civil War, around that, so between 1850 and 1900, they knew that this was like the universal fingerprint of hydrogen. That if you were looking out at the stars and you saw these colors, you knew, you look at a star and then you send your starlight through a prism or diffraction grating, and in your starlight you see these 4 colors, or 5 of them, you know that what you're looking at is hydrogen, and we still use that today. So in terms of astronomers, in terms of CSI, if you like watching that television show CSI, where they're always trying to figure out some unknown fingerprint or some unknown substance, or what was it that poisoned the victim, all that stuff. This is the kind of thing. They don't use hydrogen to poison people, but they can figure out the fingerprints of cyanide, CO2, carbon monoxide, all kinds of different all kinds of different substances, they can figure out the fingerprints. This is just the simplest set. But the question remains, all right, that's nice. You have a theory for it, but why is that the theory? You know, what is it about electrons that says, okay, you can't have any other orbits than this? You know, it's kind of arbitrary. So make a note to yourself. Niels Bohr's theory, the Bohr theory, B-O-H-R, Bohr theory was arbitrary. It worked, but it was just like saying, it was just like a board game. You know, Monopoly could be any other shape. It could be a triangle with 50 squares. Or, you know, any board, it's just, you know, whatever you feel like doing. And this is the board game that they found worked. But they didn't know why. You know, they didn't know why. But the guy that figured it out was this one, Louis de Broglie, a French chap from Paris, France. And this question that we've been asking, you know, why is an atom stable? Why is that? You know, why doesn't it radiate all of its energy away? Why is there a certain number of photons that you get? Okay, you jump down from n equals 4 to n equals 2. Good, photon, nice. Aqua color, H beta. And then let's say you drop down from n equals 2 to n equals 1. That's probably going to, I'd have to look it up, but I think that's going to be an ultraviolet. Okay? But then from n equals 1, you can't go any further than that. Why is that? This is the guy that figured it out. And his theory was this. He said, you know, it does click. It makes sense. If an electron, don't think of it like a little planet, like a little particle. Think of it like a wave. Think of it like a wave in some weird ocean. A wave, an electron wave. And if you do that, you will exactly get the Balmer series and all the other radiation series for hydrogen and all the other atoms. So let's take a look at what he said. So this is what he came up. This was his answer. How does nature select those orbits? They select them in this way. By looking at the electron as a wave or having wave properties, or as they call it, the de Broglie hypothesis, that electrons behave as waves. So exactly what did he mean? Here's a picture, and you can see a lot of pictures around the internet. You know, just type in de Broglie and then standing wave, and you'll see something like this. This inner picture shows a standing wave, kind of like those ones we did up in front of class a few weeks ago. And we got the fundamental, and then we got the first excited state. And the fundamental is like the ground state. Here's the ground state here, right down here. Here's the first excited state. This is n equals 2, right here. And what it means is that instead of a standing wave going point to point in a straight line, like what we did, he said, think of that electron as bound, and that the wave, the oscillation, is going around the nucleus. And if you have it at a certain radius, that wave will have just enough energy to make, and just the right frequency, just the right wavelength, to make one full lap, or to make 2 full laps. And if you make 1 full lap, you get constructive interference. If you make 2 full laps, or 2 full oscillations, I should say, you get constructive interference. Okay, so this is the ground state, or the fundamental mode. This is the n equals 2 state, or the first excited state. We don't normally call these harmonics. That's usually with sound and electromagnetic signals and stuff. But first excited state, yes, n equals 2. n equals 3, second excited state. And we did that. And remember, the wavelength was a little bit smaller. Between the 2 endpoints of that spring, we had 1.5 waves. We had 2 dips and a bump. But for first excited state, we had exactly same distance, but one full oscillation, a bump and then a dip, or a dip and then a bump, okay? And so same distance, and then the fundamental mode, same distance again, we only get either a bump or a dip, you know? And so same distance, different wavelength, and you can see that here. So de Broglie said that constructively, an electron constructively interfering with itself. Whoa. A wave constructively interfering with itself. We still trying to figure what that means, but it does work. It makes sense. If you do think of an electron as a wave, this all works. It's also true on guitars, so go ahead and make a note. You know, you think about it, you have a guitar, and I bet most of you have seen people tuning your guitar. You know, you have your little device, and you tighten the string or loosen it a little bit and try it again, see if it matches the right pitch, and then you tighten it or loosen it again until everything's, do that for all 6 strings. You get 6 precise notes, your guitar is tuned. So if you go one string at a time, that guitar is only going to produce one note, one pitch, one frequency, one wavelength in its fundamental mode. Let me repeat that. It's pretty important. A guitar, when it is tuned, and actually even if it's, it has to be tuned. A guitar, when it's tuned, will produce one note for each string. So here's the progression. One note, one pitch. Now pitch is the same as frequency. So one note, one pitch, one frequency. And since it's a wave, frequency, if you know the frequency, you know the wavelength. So here it is. One note, one pitch, one frequency, one wavelength. So the size of your guitar, and also, you know, the density of the string and how tight you tighten it and stuff like that, that controls the notes that you get. And if you have a good guitar, it'll sound sweet. And everybody knows, you know, a violin is, you know, like a guitar. I mean, it's a stringed instrument. It's similar structure. A violin has much shorter strings. But then if you take a cello, it's got much longer strings, and a bass has got even longer strings. And why do they call it a bass? Different pitch. Those strings, same kind of string, but it's a little bit bigger, and they put out deeper bass notes on and a cello is kind of in between a bass and a violin. And a guitar is over here, and a bass guitar is going to have different kind of strings. Anybody here play bass guitar? Okay, in the green shirt, what's your name again? Abram. Your bass guitar, does it have different strings than a regular guitar? In other words, could you use them on a regular guitar if you had to? Why are they different? Why is the bass guitar different? Okay, the strings are a little bit bigger, and so that means they oscillate at lower frequency, deeper notes. That's cool. Good. Now, I want to draw your attention to one more thing. There's another variation of this diagram. There's diagrams like this: de Broglie, standing wave, electron. Just do a search on that, and you'll see it. Figure 8.5 in your e-text is also pretty good. It's fairly simple. It's not as fancy as this one. Now, de Broglie had to have something to calculate. Now, how do you get the frequency? How do you get the wavelength? Well, here's what he said. He said, if you use Planck's radiation constant, h, and divide that by the momentum, where he got this, I cannot tell you. This was like his insight. Divide Planck's constant by the momentum of the particle, and you'll get the wavelength of the particle. Oh, did I say wavelength of a particle? Yes. Electrons are these and everything in the quantum world are these strange, beautiful, unusual creatures that behave like a particle, like a baseball going out to the outfield under certain conditions and under certain observations. And then they behave like a wave under other conditions. So the momentum state controls the size of the wavelength. Here's the formula. Lambda is equal to h over p, and h is Planck's constant, which we've talked about before. So if you think about it, Coulomb interaction, energy, and momentum if we want to figure out momentum. It's a little tougher, but you can do it. Momentum state known, Planck's constant known, ding, you have your wavelength. All right? And all this worked out perfectly for hydrogen. You know, they were astounded. Now, I'm going to add one more thing. You may say to yourself, Dr. B, how can a particle behave like a wave? How can you have a wave particle? Matter of fact, you'll sometimes see on these websites, popular science websites, they'll use the phrase wave-particle duality. But really, that's a misnomer. You shouldn't say, well, they're not, it's not like, two different things. It's one thing. It's an electron. And it is a particle that behaves like a wave. It's one thing, and it doesn't come in two flavors. It's like two flavors at the same time. So it's kind of like a smoothie. I haven't had breakfast yet. I'm still kind of hungry. So it's kind of like, you know what it's like? It's like a pizza with different kinds of, But you know what it's really like? A wave is hard to localize. You can say, well, where does the wave start? Where does it end? It's hard to spot. But a baseball, a particle, we model a baseball or a rock falling off the cliff as a particle, a Newtonian particle. But we don't model it as a wave. But electrons are modeled both ways. And so what it really is, and you have to say that it is both things at the same time. Now, a particle, a baseball, and an ocean wave, what? That's, how can they be, they can both be different, but how can they both be, one thing be just like, a baseball and an ocean wave? Well, electrons can. So here's what I always say. In the quantum world, an electron, or another particle like a proton, it behaves as a particle and a wave. It is a particle and a wave together. And it is not something that we can understand in ordinary, everyday terms, because a baseball and a wave put together, it's like saying that it's like saying, I have a bookcase that is also a horse. All right, so there's your notes. The wave-particle duality. Write down wave-particle duality, cross it out, and then write down a bookcase that is also a horse. Now, we wouldn't expect to see that here in... We wouldn't expect to see that here in everyday life, because a bookcase is not like a horse, except they both have mats, I guess. But a horse is hard to localize. We're not done. horse running around the pasture. Where is it? Oh, you got to look. Where is it? Okay, it's over there. You know, a bookcase. There it is. It's got books on it. Take them out. You know, put them on. Completely different. Now, this equation is known as the de Broglie relation. So add that to your notes. Lambda equals h over p. That's the de Broglie relation. And I'm going to give you some homework tonight about it. And let me just add one more thing. When de Broglie made this hypothesis, he was able to make our most profound explanation of the quantum world. And when he did it with this equation, he made Planck's constant to be the one constant that rules them all. Because everything in the universe obeys de Broglie's property, his hypothesis. And therefore, it is ruled by Planck's constant h. One constant to rule them all. All right, homework tonight. I'll try to get it ready for you by supper time. Come on up to the front if you want your printout. Hey.
I missed my printout. I can't.
Yeah.